NASA's twin Voyager probes, launched in 1977, amazed the world with their historic journeys to Jupiter, Saturn, Uranus, and Neptune. Both probes continue their trip into interstellar space 45 years later. Researchers, some of whom are more recent than the spacecraft, are currently using the Voyager data to unravel mysteries within and beyond our solar system. In many ways, NASA's twin Voyager spacecraft have evolved into time capsules of their age. They contain around 3 million times less memory than contemporary cell phones, transmit data at a rate about 38,000 times slower than a 5G internet connection, and each one has an 8-track tape recorder for data storage. The Voyagers are still at the forefront of space exploration despite these limitations. What are they doing right now? What will the Voyager spacecraft encounter next? Let's find out. Two of the most amazing spacecraft ever launched would never have taken flight if the stars hadn't lined up in this instance. The 4 largest planets in our solar system were the stars. As a result of this rare planetary alignment, a spacecraft could gain speed from the gravitational pull of each large planet it passed, as if being pulled along by an invisible rope that suddenly broke, sending the probe flying on its course. One drawback, though the alignment only took place once every 176 years. A spaceship would need to be launched by the mid-1970s in order to reach the planets while the lineup was still in effect. NASA created 2 spacecraft to make the most of that once-in-a-lifetime chance. Within 15 days of one another, Voyager 1 and Voyager 2, identical in every way, were launched in the summer of 1977. They have been operating in space for almost 45 years and send data back to Earth every day from the solar system's farthest known planets. They have lasted longer than any other spacecraft in history and have traveled farther. According to our best understanding of the dividing line between the Sun's sphere of influence and the rest of the galaxy, they have entered interstellar space. They are the first objects created by humans to do so, and they will continue to hold this distinction for at least a few more decades. Overall, not a bad record, given that the Voyager missions were initially only intended to last 4 years. The Voyager spacecraft's early observations of Jupiter's and Saturn's moons, which stunned researchers 40 years ago, revealed the presence of active volcanoes and inferred ice fields on worlds that astronomers had assumed would be as inactive and cratered as our own moon. Voyager 2 was the first spacecraft to pass by Uranus in 1986, and 3 years later it flew by Neptune. It is the only spacecraft to have traveled in this way so far. Currently, they are surprising physicists with unexpected discoveries about unexplored regions as pioneering interstellar probes more than 12 billion miles from Earth. Finally, their amazing voyage is nearing its end. NASA has turned off heaters and other non-essential components during the past 3 years to stretch the spacecraft's energy reserves as far as possible, likely until 2030. This is a bittersweet moment for the scientists involved, many of whom have been part of the expedition from the beginning. They are now faced with the completion of a project that has far exceeded their expectations. Voyager 1 arrived at Jupiter 546 days after its launch in March 1979, and Voyager 2, on a different course, arrived in July of that same year. Both spacecraft were equipped with Vidicon cameras, which used red, green, and blue filters to create full-color images. They were designed as stable platforms, with a rotation velocity over 15 times slower than a clock's hour hand, to prevent visual blur. The spacecraft began transmitting images of Jupiter even while still 3 to 4 months away, delighting standing room-only crowds at NASA's Jet Propulsion Laboratory JPL. It was an unexpected surprise when Io appeared in color. Prior to the Voyager missions, it was believed that all moons in the solar system would look similar, drab and cratered. The incredible diversity of moonscapes the Voyagers found near Jupiter and Saturn was unanticipated. The first clue that there might be more diverse moons than astronomers had imagined came when the Voyagers were still 1,000,000 miles away from Jupiter. One of their devices, the Low-Energy Charged Particle LECP detection system, picked up some unusual signals. Io had active volcanoes, as revealed by the onboard cameras. Io, slightly bigger than Earth's moon, is now known to be the solar system's most volcanically active body. The components ejected by Io's volcanoes are responsible for its vibrant hues and the anomalous ions that strike instruments like LECP. The greatest of Io's volcanoes has produced plumes 30 times higher than Mount Everest, with an ash field almost the size of France. Voyager spacecraft captured more than 33,000 images of Jupiter and its satellites in total. Every photograph seemed to reveal something new. Jupiter had rings, and Europa, one of Jupiter's 53 named moons, had an icy covering that was shattered. The ice is now believed to be more than 60 miles thick. The spacecraft received a 35,700 mph farewell kick as they left the Jupiter system, thanks to a gravity assist. Without it, they would not have been able to escape the sun's gravitational pull and travel to another star. The Voyager spacecraft split off at Saturn. Voyager 1 passed by Titan, the moon cloaked in orange smoke, and then turned north away from the plane of the planets. Voyager 2 alone went on to Uranus and Neptune. In 1986, Voyager 2 discovered 10 new moons orbiting Uranus, bringing the planet's known moon count higher. 3 years later, Voyager 2 recorded the fastest wind speeds ever observed on a planet in the solar system, up to 1,000 mph, while passing 2,980 miles above Neptune's azure methane atmosphere. Triton, Neptune's largest moon, was found to be one of the coldest locations in the solar system, with a surface temperature of 391 def 235 C. Nitrogen gas and powdered particles were ejected 5 miles into Triton's atmosphere by ice volcanoes. If Carl Sagan, an astronomer on the mission's imaging team, had not been involved, Voyager 2's pictures of Neptune and its moons would have been the last ever taken by either spacecraft. NASA originally intended to turn off the cameras after the grand tour was completed. There would be no photo opportunities beyond Neptune, only the endless nothingness of space and impossibly distant stars. Despite this, the mission was extended, renamed the Voyager Interstellar Mission, and Sagan persuaded NASA leadership to order Voyager 1 to take one final set of pictures. On Valentine's Day in 1990, the probe pointed its cameras back toward the inner solar system and took 60 final images. The most famous of these was the pale blue dot showing Earth from 3.8 billion miles away. It remains the farthest image of our planet ever captured. Earth appears barely visible, a tiny speck hidden by sunlight reflected off the camera's optics. Now, both Voyagers are so far from Earth that a one-way radio signal traveling at the speed of light takes almost 22 hours to reach Voyager 1 and just over 18 hours to reach Voyager 2. The spacecraft advance by 3 to 4 light seconds every day. The NASA Deep Space Network, a trio of global tracking facilities, is their only connection to Earth. As the Voyagers move farther away, their signals become fainter. The world is noisy with signals from radios, televisions, cell phones, and more, making it increasingly difficult to hear these faint transmissions. Yet even these whispers have challenged and reshaped what astronomers expected to find as the Voyagers moved into the interstellar portion of their journey. It's important to distinguish between the solar system's boundary and interstellar space. The Oort cloud, a distant collection of comet-like objects held by the sun's gravity, may extend halfway to the nearest star. It will take the Voyagers another 300 years just to reach its edge. However, interstellar space begins much closer where the solar wind ends. This outflow of charged particles and magnetic fields from the sun, known as the solar wind, expands outward at hypersonic speeds, forming a bubble called the heliosphere. Eventually, the pressure of interstellar matter slows this expansion, creating a boundary called the heliopause, which the Voyagers crossed. Before their journey, estimates of the heliopause's distance varied greatly, but now, thanks to these pioneering spacecraft, we have a clearer understanding. Assumptions: one early guesstimate located the heliopause as close as Jupiter. Garnett's calculations from 1993 put the distance at around 25 times further, between 116 and 177 astronomical units. 1 AU, or 93 million miles, is the distance between the Earth and the Sun. Garnett's projections from 1993 were accurate before one of the Voyagers ultimately reached the heliopause. About 20 years had elapsed. Voyager 1 had actually detected the anticipated rise in plasma density. Its plasma wave detector had inferred an 80-fold increase. But there had been no indication of a shift in the ambient magnetic field's direction. Shouldn't that change have been apparent if the vehicle had traveled from a place where the magnetic field originated from the sun to one where it came from other stars? That was a shocker. In November 2018, Voyager 2 arrived at the interstellar seashore but did not notice any magnetic field changes when the spacecraft reached the heliopause at 120 astronomical units from Earth, the same distance reached by its twin 6 years earlier. It added still another riddle. All theoretical models predicted that the heliosphere should ebb and flow in time with the sun's 11-year cycle, but this did not fit any of them. The solar wind was at its strongest when Voyager 2 arrived, and if the predictions were accurate, the heliopause should have been further out than 120 astronomical units. theorists' models of the interaction between the heliosphere and the interstellar environments are getting more intricate now that the Voyagers are providing them with some actual field data. According to the general image, our sun left a hot ionized zone and entered a patchy, partially ionized section of the galaxy. The hot zone probably developed as a result of a supernova, an ancient star nearby, or perhaps several exploded at the end of their lives, heating the surrounding area and removing electrons from adjacent atoms in the process. One way to conceptualize the boundary enclosing that area is kind of like the seaside, with all the water and the waves whirling and mixing together. Magnetic fields twist and turn because we are in that sort of tumultuous area. Although the degree of turbulence observed can vary depending on the method of observation, it is not like the smooth magnetic fields that theorists typically prefer to draw. As a result of the heliosphere's influence on the interstellar medium, the Voyager data reveal numerous small-scale changes near the heliopause but negligible field variations at vast scales. It is anticipated that the spacecraft will eventually leave those turbulent zones behind and come into contact with a pure interstellar magnetic field. Saying goodbye to these innovative spacecraft won't be simple. Seeing things come to an end is difficult. There are currently 5 operational instruments aboard Voyager 2 and 4 on Voyager 1. They are all propelled by a mechanism that transforms heat from plutonium's radioactive disintegration into electricity, but NASA has been forced into triage mode as a result of the power output diminishing by roughly 4 watts annually. The Voyager's adventures will continue even when they are entirely silenced. Voyager 1 will pass Proxima Centauri, our closest neighbor star, in 16,700 years. Voyager 2 will follow 3,600 years later. After that, they will spend millions of years orbiting the galaxy, long after our sun has disintegrated and the heliosphere has vanished, not to mention one pale blue dot. They will still be there, largely undamaged. They might be able to deliver a final message at some point throughout their journey. However, it won't be broadcast over the radio. If it is, it won't be by humans. 2 recordings, another form of antiquated technology, are used to convey the message. But not your typical plastic version. These are formed of copper, have a gold coating, and are enclosed in aluminum. Images and noises intended to provide a feeling of the world the Voyagers came from are encoded in the grooves of the golden records, as they are known. There are 90 minutes of music, including Bach's Brandenburg Concerto No. 2 and Chuck Berry's Johnny B. Good, as well as images of kids, dolphins, dancers, sunsets, and sounds of crickets, rain, and a mother kissing her child. Jimmy Carter, who was President of the United States at the time the Voyagers were launched, also left a message. We cast this message into the cosmos. It reads in part, "We hope someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope, determination, and goodwill in a vast and awesome universe. Thanks for watching another episode." While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.